Okay, week 10, just got one more week, almost there. So we're wrapping up chapter 6 today, 6b and 6c. I think it skips some of the sub-chapters like 6.7. Again, the way chapter 6 layout is very similar to chapter 3. You know, you get 3a, 3b, 3c. It's the same here. We're still working with energy and then on to momentum. But now we're dealing with non-particles. We're dealing with rigid body. So you have to consider the alpha and omega. Kinetic energy, so conservation of energy. Sometimes we represent some of the work done for, say, weight and also spring with potential energy. Again, don't duplicate them. And also never, never, never use energy approach for collision. It will not work. It will crash and burn. The idea when you have a system of particles, you just basically sum them all up. You calculate them separately first, you know. Don't add the mass and then, you know, multiply it by the velocity. Do you have mv squared for each of the particle? Then sum it. However, that's only for particles. If we think about the definition for particles again, is that we don't care about self-rotation of a particle, and it's also negligible dimensions. That doesn't really apply to rigid body. So to upgrade the equation for rigid body, we basically have like an additional term. Instead of just half mv squared, we have half mvg squared. So vg, the velocity of gravitational center. This is basically just the same as, you know, your normal particle kinetic energy equation. But we also have a second term, our ig, half ig omega squared. So the ig, mass moment of inertia, again, you can kind of think of it as a angular mass, and then omega, angular velocity, kind of equivalent to your basically vg. Questions so far? Okay, pure translation, this is what we're used to, just going in a straight line, nothing fancy. If there's no rotation, then, you know, omega becomes 0, then we're just left with our half mvg squared. Pure translation, this actually happens quite often. So it's basically just rotating with respect to its own self. So the gravitational center, in this case, overlaps with the axis of origin or rotation. When that happens, because v is equal to r omega, and if you do the distance r, let's say from r o to rg, it's going to be 0 because you overlap, then your half mvg squared becomes 0. Then you're left with only the rotation aspect, which is our half ig omega squared. The third case is, this is actually quite popular when you have some kind of rod fixed on one end. So it's kind of like a fixed axis rotation, but it's not fixed with respect to its own gravitational center. So now O is no longer directly on top of G. Now when that happens, you basically have both Vg and also Ig omega. So both terms are not 0. However, you can actually kind of work around a little bit because Vg is r omega, so you can actually plug it in and simplify the kinetic energy to this half I naught omega squared. This is a very, very convenient form. If you can use it, you should always use that form. Again, it's the same as that, but it's built in. If it's built in, there's less chance of something goes wrong. Questions? Okay. Work done. So there are some forces that don't do work. Normal reaction is a great one because work done is basically force times displacement. If you have a normal reaction, especially let's say, you know, resting on a block, if there's a displacement, then it's levitating. There's no longer normal reaction. Another great one is friction when there's no slipping. So when it's just rolling without slipping, basically at the contact point, the velocity is 0. technically there's friction to prevent it from slipping, but let's say, you're looking at this point, yeah, there's friction, but a fraction of a second later, it's right there, right? It gets rolled up, it's not touching anything, there's no friction. So if you assume the contact time is like 0.0001 second, the work done is negligible. But if they're slipping, then that gets a lot crazier. Questions so far? Okay. Internal forces do no work. So some of you may remember the truck problem from last week. The very overkill truck problem with the kind of like what's called the spool on the back. When we draw the FBD, the spool has a normal reaction forward. That's pushing the spool forward. But when we draw the FBD for the truck, it kind of flipped direction because this is an internal force, opposite direction but same magnitude. It cancels each other out. So we don't consider internal force in work done. Just a summary slide. Again, very, very careful not to confuse your IO and IG. And here again for the rods, this is how you go from IG to IO, 1/3 ml squared. Questions so far? Okay, momentum. So linear momentum, mass times velocity. When you have rigid body, you use the gravitational center's velocity, so Vg. Similarly, for angular momentum, instead of like say having a mass, we're going to have Ig, which is your mass moment of inertia at its gravitational center. Again, very careful the subscript. Hg and Ho are different. Sometimes, if it's self-rotation, then it's going to overlap. But let's say if it's like a, connected to a rod situation, then that's not going to be the same. Pure translation means no angular momentum, pretty straightforward. Rotation, fixed axes, again, this is what you'll probably be running into more. And really, H0 equals I naught omega is what you primarily want with these kind of rod system. Again, you do have to probably apply parallel axis theorem. Questions? Okay. Oh, it's general motion. So this is the trickiest one to deal with. The idea is that you basically combine your linear momentum with your angular momentum, but you don't just plug the linear momentum in, you have to put your D in, and then that gives you, like in this case, this would be, instead of, let's say, having it as A, this is O, then this is basically HO equals IG omega plus MVGD. The D is still similar to what we ran into the last 2 weeks, where it's basically you draw the velocity from the gravitational center, you extend it until it hits a perpendicular line, then that is your distance D. Looks like an A there. And if you compare it to the equation last week where we look at the sum of moment, the equation is actually quite similar. But you basically downgrade it from alpha to omega and from Ag to Vg. Again, momentum is mass times velocity, but the sum of moment is actually the impulse. So this is why you have to basically integrate it, one side of it with respect to time. If it doesn't make sense, it's fine. The equation, just follow it, it will work. Questions? Okay. Again, just a longer summary slide. The only thing I want to point out is the conservation of momentum. When we say it's conserved, that means mass times velocity at start equals mass times velocity at the end. If there's an impulse, then it's no longer conserved. It's a impulse momentum equation approach, where we have basically either your moment or forces. So do not confuse the angular momentum conservation with the impulse momentum equation. Because if they ask you if angular momentum is conserved, you say yes, and then you put impulse in, then there you go, you lost a couple of marks. Okay, questions before we get started with the first problem of the day? Okay, so the problem is given in imperial unit, but that's okay. We're just gonna swap everything to metric right away. So m is equal to 91 kilograms. RK, radius of gyration is 0.1 meter. Initial velocity is 0.61 meter per second. 24 inches becomes 0.61 meter. There's a bit of a neat trick for basically estimating from, say, inches or feet to a meter. This is not official. If you're doing assignment, then Google is going to be a lot more accurate than this. But 12 inches is basically, well, not roughly, it's exactly 1 feet. Now, 3 feet is roughly 1 meter. Very roughly. I think technically it's like 3.1 or 3.3, but if you just hear like, oh yeah, the plane is cruising at 30,000 feet, you can quickly just divide by 3 and go like, okay, it's cruising at a 10,000 meter height. Not good one. I think 2 pounds, roughly 1 kilogram. Again, technically it's 2.2, but gotta do some quick math. These are handy. This is just for quick reference. Do not use this for assignment or future courses. They'll get anal. They like the precisions in academia. So 12 inches, 1 feet, 0.3 meter. The wheel also has a radius, which I'm going to call R, of 6 inches or 0.15 meter. So one of the tricky part about this problem is that they gave us a radius of gyration, but also the wheel has a radius. So again, the radius of gyration is primarily for calculating mass moment of inertia. It sometimes doesn't even have to resemble the physical geometry. Sometimes we don't have to consider the physical geometry, but in this case we actually do, because the wheel is rolling down, so that radius has to be conserved. Questions so far? Okay. The question says no slip, which is good. As far as friction does no work. This means we can use our favorite energy approach. T1 plus V1 equals T2 plus V2. But there's actually a lot of unknowns that we have to calculate, and primarily with trigonometry. This is kind of about where the dynamic side of the question take a pause for the next 10 minutes and go into full math mode. Okay. We need some sketch. So this is at the start. We have basically point A down here. There's a bit of a, I guess like a quarter circle, quarter pipe. And then it goes up a straight ramp at C. We're given theta. This is actually perpendicular to basically BC. This allows us to actually get this angle to be theta as well. The disk is basically sitting like that at R, and then when it finishes, it's going to be around here. So B, C. So I'm just going to use dot to present basically their old location, or the location that they have to pass through at a certain time. The problem or the trick with this one is the gravitational center, because you need to actually find a change in the gravitational center's altitude to find the potential energy. And to do that, there's quite a bit of trigonometry. First of all, we're going to call it our delta H1. And then from B to C, that's going to be our delta H2. Now, delta H1 is actually pretty straightforward to calculate. We have theta, and this height is actually also delta H1. The reason is that, it's kind of on the same angle, right? So as it moves down, it's basically moving. The loss of altitude is the same as the change of the height of the triangle underneath it. So you can just directly calculate the height of that triangle and then apply it to the change of gravitational center from C to B. Questions so far? So, where is it? Okay. Delta H1 is pretty straightforward. 0.3 sine 30 degrees. 0.3 being BC. Now, finding delta H2, that's the trickier bit. So instead of going all the way to A, we're just going to stop at the gravitational center, G here. This is because, it actually doesn't end up going to point A because of the clearance. Again, we're tracking the gravitational center. In the past, we track the particle where there's basically no dimensions to it, or thickness, or radius. So therefore, we can just slap it right on. But in this case, rigid body, we have to consider the tolerance. Now, we know this distance OG, which is basically just OA minus RR. Now, if we look at basically relative to B, so this would be A, on the right would be B. This is also OG because this is basically kind of like I guess like a quarter pipe, 1/8 of a circle. And the idea is that this is your delta H2. But to find that, we also have to define a new height, our H3. And to find H3, that's not too bad. We got theta, we have this length OG, H3. That's going to give us H3 equals OG cosine theta. Now you can sub the OG equals OA minus RN, but we're going to save that in a couple steps later. And finally, to find delta H2, we basically just get delta H2 equals OG minus H3, or OG times 1 minus cosine theta. And then now this would be a good time to actually sub it in, but we're going to put it in when we actually construct the equation. Questions so far? So when I was presenting this from out of class on Tuesday, I think upstairs, BA 2159, this is the point where the fire alarm actually went off. And then we all went outside. And then 10 minutes later, I think the fire alarm shuts off. We all start going back in. As soon as we enter the door, fire alarm triggers again. So we went back out. Yeah, not fun. So hopefully that won't go off this time. Knock on wood. Okay, so now we can actually look back at our energy equation. Questions so far? All that is just kind of trigonometry, but now we're going back to the dynamic side of things. Okay. So we're going to make our life a little bit easier by setting datum at 8 plus R. This allows us to say that the potential energy at the final state is 0. Now, we still have to come up with the initial potential energy, which is this Rmg delta H1 plus delta H2. We don't have to include delta H3 here. That's why I kind of left it as an H3. It's just for us to find delta H2. It's going to become mg 0.3 sine 30 degrees plus 0.61 minus 0.15, 1 minus cosine theta. This is basically OA minus R. And then close the bracket, which should give you 189 joules. Again, the important thing is that you have to track the gravitational center when it comes to rigid body problem. It does turn into a lot of trigonometry, especially if you're rolling. And God forbid, if they want rolling plus slipping, then you cannot just use the energy conservation. You have to include work done. We still need initial kinetic energy, which is 1/2 mvg squared plus 1/2 ig omega squared. Again, it's rolling down, so it's going to have both vg and omega. But since no slip, our vg is just equals to r omega. This means we can rewrite it to omega equals Vg divided by R. This allows us to basically simplify or reduce the number of unknown. It might look like we had two unknown, right, Vg and omega, but in this case, we just need Vg. Yep. Yeah, so it has the, I'm assuming you're wondering why it has both terms. So in the past, we only have the blue bits because it's pure translation. But since it's rolling down, we need the omega, which is the green bit, to account for the actual rotation of the body. As a good way to visualize it is, let's say you have something spinning with respect to its gravitational center at, say, 5,000 RPM, rounds per minute. At the gravitational center, there's no velocity, but then, if it's spinning 5,000 RPM, there's kinetic energy. So the Ig omega squared, or half Ig omega squared, allows us to basically represent that equivalent of angular kinetic energy. Okay. So T1 becomes half mvg squared plus 1/2 mk squared times vg squared divided by r squared. Again, we're given the radius of gyration. When they do that, life is simple. Just do mk squared. And we can clean this up one extra step by taking out m Vg squared. And we're going to call that 1 because that's the initial, into 1 plus k squared divided by r squared. Where Vg1 is just equals to V1, giving us T1 is equal to 24.5 joules. Questions? Again, because there's no slipping, we basically just got rid of omega. Now, the reason why we neatly wrote it out this way is that this allows us to also write an expression for the final kinetic energy. And all we have to do is just replace Vg1 with Vg2. We can do this because the problem started by rolling down, and at the end, technically, is still rolling down or rolling. So this is a completely legal operation. You can do the whole derivation again. It's just going to give you the same thing. Which is going to give us a T2 of 65.7 times V2 squared. Finally, we can put everything into our energy equation. Questions on T1, T2? Yep. How do I came up with V2? T2? Yeah, so it's the same thing as what we did for T1. All the way up to basically, this line, we haven't put in Vg1 yet, right? This operation, this is just a way to express our kinetic energy of the system, or in this case, the body. As long as it is still rolling, which has the, the Vg and also the omega, then this equation still holds. Now, at the end, it looks like it's basically about to roll back up, but, don't care. It's still rolling. So it's going to have a Vg, it's going to have an omega. And again, we can only do this because no slip. They're slipping, then, whew. Then an average is probably going to be like 30% for that question. Does that make sense? Okay, T1 plus V1. Okay. So again, for energy problems, don't go gun-hoing in at the beginning and just try to solve all the T1, V1 into one mega line. Always break them out. You can imagine if I try to just stuff everything and work from there at the beginning, you're going to have an equation that is like, half a page long, and that's a recipe for disaster. Okay, now V2 is 0 because we set the datum at basically where the particle ends up. This is going to give us T1 plus, well, we don't even have to write that. So 189 plus 24.5 equals 65.7 V2 squared. One equation, one unknown, giving us a final velocity of 1.8 meter per second. A good thing about separating and calculating each of the variables first is that when you combine it, things are a lot easier for the TA to track. Now, if you look at the question, it actually asks for the normal reaction, and And you might be wondering why we're calculating velocity. So this is actually a anti-coordinates problem, right? If you look at the way it's laid out, you can imagine basically that is your, that is your n, and that is your t. So if we draw our FBD at point A, you're going to have, the normal reaction n and also the weight. Now there's technically probably friction in a horizontal direction, but we don't care. That's because we just want to resolve it in the normal direction. Fn equals man, because that allows us to use an equals v squared divided by r. Right, again, an is equal to v squared divided by rho or r. The reason why I use the big R here is that this is not the same as the small radius, right? You have to look at the whole picture, where this is the actual big R from O to point G. So normal reaction minus mg equals m v2 squared divided by distance OG. N is equal to 892.7 plus 641.0, giving us a normal reaction of 1534 newtons, and voila. Questions? Okay, I'll leave it on for another 10-20 seconds, then we'll move on to problem number 2. We do have 4 problems today. All right, anyone needs more time or anyone has questions? Okay, we'll hop on to question 2. So I think it's actually quite a neat problem. I think the official solution uses a really, really weird method that I completely dislike. I'll show you what the official solution did afterwards, the typed out version. Then I looked at it for half an hour. I have no clue. I was about to give up, and then they use something from absolute motion. So you have a system. Theta is originally at 90 degrees. So again, we're going to draw it out. Never skip the FBD and also these kind of sketches. Visualization is very important in engineering. We have A here. Now A is not the same location as the gravitational center. It's B to B. And we also have a horizontal distance to B here. We're going to find a length, L1. We're also going to note this G to be M1. So the idea is that theta is going to decrease, and when that happens, our system would probably look something like that. This is point A, G. It's B here, but B is just a distraction. And then we're going to call this L2. The horizontal distance is still 2b. Now this gives us basically two change of altitude. For M2, that's going to give us a delta H2. And then for the rod, M1, we're going to have basically, let's call this the OG. That's going to give us a second, or delta H1. So mass 2 drops down, so it actually loses potential energy, whereas mass 1, the rod rotates up and gain potential energy. Now when we calculate these, later on we have to manually assign a negative sign for delta H2. The direction, these are one-sided arrow, they're very important. Now when both of them are in one direction, then you can get away with having both positive, but in this case the opposite direction. If you keep them in the same direction assigned, it's going to mess up and explode. Unless, you have it on the other side, then it's going to neglect the negative sign. Okay, questions so far? Okay, more trigonometry. Ooh. This one is a little bit simpler. So at the start, to find L1, it's pretty straightforward. Square root of 2b squared plus b squared equals b times square root 5. Now, at the finish state, it's no longer a right triangle. Got 2b. This is b, even though it doesn't look like it. And that's L2. To do that, we need the cosine rule. Again, the math document I have under the supplementary material tab on Kirkus has some examples, or at least a demonstration of the cosine rule. You should definitely have stuff like this on your crib sheet. You might not need it, you probably won't need it, but it's better to have it and to not need it than the other way around. Same thing with all the mass moment of inertia equation that I showed last week. It takes a tiny box on your crib sheet. If you don't have it, and chances are the question is not going to give it to you because that's what the crib sheet is for. Then L2 is going to give you b is equal to 5 minus 4 cosine theta. Questions? Okay. So to find H2, or delta H2, which is how far the M2 has dropped, it's basically just L1 minus L2. Because the missing rope length is just going to end up on the right-hand side. It's not going anywhere. There's no crazy looping around. It's pretty straightforward. So b squared root 5 minus b squared root 5 minus 4 cosine theta, giving us 0.202 meter for H2, or delta. We do need a negative sign, but we'll apply it later on. Questions on delta H2? Finally, we're going to also find H1. So the start state, uniform rod, 1.5B. That's not even vertical. There we go. And then at the end state, it's also 1.5B. But we're going to assign it a y1, which gives us a triangle, 60 degrees, 1.5b. This is basically O, that's your G, giving us y1 is equal to 1.5b sine 60 degrees. So delta H1 is equal to 1.5b minus y1. Sub the values in, give us 0.08 meter. That one should be positive because it's gain altitude, it's gain potential energy. So we're not going to mess with the sign, we're going to keep it as positive. Questions? Right, finally, we can plug everything into our energy equation. Oh no, I just jinxed it. We forgot all the kinetic energy components. Oof. Okay, we're going to set the datum at time 0, where theta equals 90 degrees. The system is initially at rest, so T1 equals 0. And because we set a datum at the start point, potential energy also ends up being 0. So that means we only are missing one or two terms, the kinetic energy for both particles or body at the end. V2 has two components. The final velocity for M2 and the final velocity, not the velocity. Sorry, the final kinetic energy. Oh, sorry, I messed up. Okay, this is why I don't like the annotation. Back when I did my undergrad, you use potential energy, PTE plus KE. Because now with V, the first thing that came to my mind is velocity, but it actually represents gravitational energy. You're not going to get max deducted for the method you use or annotations, but I do have to adhere to what the course or basically the textbook uses. Okay, so we're still working with potential energy. Sorry about that. The change of potential energy. So for mass 2, we have negative m2g h2. For mass 1, we have plus m1gh1. That's going to give us negative 2.47 plus 0.79, or basically minus 1.68 joules. Which makes sense. Primarily, the system is being driven by the loss of the potential energy from M2, which is what's accelerating both particles. Okay, finally, we can calculate the kinetic energy, T, which also has two parts because we're dealing with two different bodies. For the first one, M2 is just going downward. There's no omega, so we're just going to skip the omega part and just directly use V2. However, for the rod, it's rotating, so we're going to have to keep the omega. Now, because the rod is mounted fixed at one end, it's kind of like a fixed axis rotation, so we can simplify this into 1/2 I naught omega squared. Suddenly the equation isn't quite so ugly anymore. Now, again, V is equal to R omega. We're arranging. We can get omega is equal to V divided by R. It's mounted at point A, the rope. So we're going to have half mv2 squared plus half IO or I naught IO, which is 1/3 ml squared. Again, the length is the whole length of the rod. And then so omega, we're going to write VA divided by RA squared. So very important, when you use V is equal to R omega, you have to make sure that when you say you're trying to find VA, you have to keep the R as A as well. If you're trying to find VB, then it has to be divided by RB. It wouldn't work if you mix up the subscript or the length. Questions so far? So it looks like we're stuck because we don't know V2, we don't know VA. Yep. Second? Yes, exactly. So this is the part where, again, more dynamics. Oh, yes, I have the rope. Trusty rope. So if we look at the system, M2 and A are connected on the same rope, right? So I think this is your A, this is M2, and it goes around. Now, it might look like go for a bunch of stuff, but it's the same rope, right? If I pull here at 1 meter per second, here it's going to be 1 meter per second, right? So if I'm pulling M2 with V2, VA is going to be the same velocity. It's the same rope. There's no funny things going on. So this gives us the missing piece where V2 is equals to VA, and suddenly one equation, one unknown. Again, the rope is tied at A. Questions? With L equals 3B, that's going to give us a T2, 1.25 divided by 2 V2 squared plus 1 divided by 6, 9B squared. V2 squared divided by B squared cancels out. T2 is equal to 1.125 V2 squared. And for the third time, finally, we can actually plug everything into our energy equation. Again, start at rest, so no initial kinetic energy. We set a datum at starting point, so left hand side 0. On the right hand side, our T2, V. So we get 2.125 V2 squared minus 1.68, giving us a V2 of 0.89 meter per second, which is also equals to VA. Finally, VA is equal to RA omega, giving us omega equals 2.22 radian per second. So again, you can gun-ho in trying to populate this energy equation from the get-go. Not recommended. It's better to do the hard work calculating everything separate. Then when you construct the energy equation, it becomes the easy part. Questions? Okay. I'll leave it on for another 10 seconds, then I'll show you the official solution. they use a very weird method that I don't like. We usually do like a 5-10 minutes break after the second question. So, okay, any questions? Anyone needs more time to copy this down? Yep. Yep, right here. Again, we're assuming that it started, basically we're assuming the start location has zero potential energy. That's why usually you wouldn't have a negative sign, but I don't like chopping them up. Good? It should work. It matches with the solution.